All right. Hello, everyone. Welcome to this week Autonomy Talks. This week is a pleasure to have Margarita Grinvald, who is a PhD student in the Autonomous Systems Lab at ETH Zurich, working with Professor Roland Sigve. Something about her. So she before moving to Zurich, she obtained her bachelor degree in informatics from the University of Lugano. She then received her master's degree in robotics systems and control from ETH Zurich. And among other activities, she co-organizes the Zurich Computer Vision Meetup. So her research interests include robotic perception and computer vision, with a specific focus on semantic mapping of complex real-world environments up to the level of individual objects. And this will be the topic of today's talk, and we are very happy to hear what she's going to talk about. So very happy to have you here, Margarita. Go ahead. The stage is yours.
Thanks a lot. So hi, everyone. I'm Margarita. It is a pleasure to be here today, even if only virtually. So I would like to ask you to use your imagination and pretend that this event was being held in person. I know it feels like a long time, but try to use your imagination. And in particular, try to imagine how the conference room that we will be sitting in would look like. Perhaps something like this. Now, as you watch in this sequence, your brain can't help but immediately start to build some sort of 3D map of that room in your head. And in the same way as humans can construct such models of the surrounding scenes in our mind, a lot of research has looked into enabling machines to be able to build their own digital representations of the physical world. And so here's what the output of one such scene reconstruction method could look like for the video sequence that you just saw. We can observe that the model succeeds at capturing the 3D geometry of the scene together with appearance and color information. But if we were to ask, besides how the room looks like, does this model contain any information about what is in the room? In other words, is there any real understanding of the different objects in a scene and what kind of objects are those? It turns out, if we were to visualize any high-level semantic information that traditional scene reconstruction provides, there is simply none. Beyond geometry and color, there is no interpretation of the different parts of the scene. So next, research focused on encoding some form of understanding or meaning into these models of the environment. And a class of techniques that go under the name of semantic mapping can now classify scene parts by their category. As an example, all the chairs in the 3D model will have the semantic class chair, shown here in red. Great. So is this enough to compare machine perception to human vision? We believe not. And the reason is that standard semantic mapping can tell us that there are chairs in the scene and what parts of the scene all the chairs collectively occupy, but it says nothing about how many chairs are in the scene. And most importantly, it cannot tell apart one chair from the other. In contrast, a desirable digital model of the environment for many robotic applications will be one that not only classifies each part of the scene by its corresponding semantic category, but also encodes knowledge about the individual instances of a same category. Think, for example, of a grasping and manipulation application, where knowledge about an individual instance is crucial for targeting the interaction at a specific object. Or even in an autonomous driving scenario, knowledge of the 3D shape and location of all the other cars on the road can help us to reason about things such as motion and occlusion, compared to simply knowing that there is some indefinite number of cars on the street. So this task of mapping at the level of individual objects is known as instance-aware semantic mapping, and it is precisely the topic of my today's talk. So instance-aware semantic mapping does indeed add one more level of complexity compared to traditional semantic mapping. But we are convinced that awareness of object instances or individual objects of interest in the scene can really bridge the gap between robotic and human perception. So these are some of the key ideas behind the two works that I would like to present today. And these works have been carried out jointly with my colleagues at the Autonomous Systems Lab at ETH Zurich under the supervision of Professor Roland Sigve. And so the first of such works really wants to explore in depth the topic of online instance-aware semantic mapping of real-world environments. Now, what is the one thing that clearly differentiates real-world environments from other perhaps more controlled environments like the one of our robotic research lab. So a key property of the real world is that it exhibits open set conditions. So this means that as the autonomous agent is traversing the environment, the scene elements, the objects that the agent might encounter and observe, are not limited to a predefined set of object categories. The agent instead is very likely to encounter novel and previously unobserved elements. Let me illustrate this with an example. Here is a top-down view of the 3D reconstruction of a real-world office room. We can see, if we take a closer look, that the scene contains objects from some quite well-defined categories, such as chairs, but also there are some scene parts which exhibit clutter. So there are some elements which have not been previously observed. For example, we as humans can immediately tell that on the desk in front of the chair, there is some box-like object. And even though we do not know exactly what kind of box that is, we can tell that it does not belong to the table and it's a separate object. And so in the same way, we would like our algorithms to also be able to detect and map such object, even though this particular instance of a box has not been encountered before, for example, during training. So at the core of our approach is the use of RGBD cameras. So RGBD cameras differ from standard cameras in that besides the color information, they also provide depth information. So for each pixel in the depth image, the camera is going to give us the distance to the observed surface from the sensor. And here in the bottom is visualized as darker green, closer surface, brighter yellow, further away surface. So we assume that our sensor is localized in 3D space, either by a third-party module or thanks to the ground truth poses provided with some dataset. So as this stream of RGBD image pairs is coming in, we decide to process this information with the 2D segmentation approach, which I'm going to talk about in more detail in a second. But for now, all we need to know is that processing each incoming RGBD image pair independently one from each other can of course yield inaccurate or even inconsistent results from one frame to the other. So we propose to incrementally fuse such partial and inconsistent per frame segmentation results into one single consistent 3D model, which in our case is a truncated sign distance field volume discretized into a 3D voxel grid. And so over time, by fusing inconsistent segmentation information from multiple views into a single model, we're able to converge to a stable and consistent instance-aware semantic segmentation of the environment. So let's take a closer look at how we actually process our multimodal sensory input. We process the color and the depth frame in parallel and independently. The RGB frame is fed into an off-the-shelf 2D instance-aware semantic segmentation network, which is known as MaskerCN, which is able to detect individual object instances in the color image, and then it can provide for each of the detected objects a per pixel segmentation mask, a classification label, and a classification score. Now, MaskerCN is very powerful and of course also very popular, but the issue with the predicted masks is that they often do not reflect the true boundaries of the corresponding real-world objects. So the mask edges might either bleed into the background or undershoot with respect to the true contour of the object. So let's keep this in mind for a second and talk about how we process the corresponding depth frame. Here we adopt an unsupervised approach, which is based on a core assumption that for man-made objects, convexity is a minimal requirement for objectness. So to exploit this assumption, we first estimate for every point in the depth frame its normal, and then we perform an analysis of such normals to identify concavities that separate two or more convex regions. And it is at these concavities that we perform a segmentation cut. So we split the depth image into a set of convex segments. And a sample output of this approach will look something like this. As you can see, this method decomposes the depth image exhaustively into a set of convex segments, and the edges of these 2D segments accurately reflect the geometry of the object. But because of the simplistic convexity assumption, it naturally results in oversegmentation of non-convex articulated objects, such as the chair shown here. Now, given these two very different but complementary approaches to processing color and depth information, we decide to combine the two segmentation results with a simple 2D overlap measure in the image frame, which essentially matches the convex geometric segments to the semantic masks that overlap the most, if there are any. So the goal is to obtain a per frame segmentation that combines a classic computer vision approach with deep learning and then retains the best of both worlds. So the final result then is a set of convex segments that accurately reflect the edges of the corresponding real world object. For some of them, we have a semantic category information if a semantic mask has been associated with it, and we no longer suffer from over-segmentation of articulated objects. Now back to the office space that we have seen before, let's see our framework for incremental instance-aware semantic mapping in action. As the RGBD stream is processed with the two independent approaches we just talked about, the per frame segmentation results are then associated over time and fused into a single 3D volume, which is here visualized on the right as a color mesh, which has been extracted from the TSDF. And the different colors here on the right do not have any particular meaning except the fact that they represent different object instances. So the more RGBD frames are processed, segmented, and fused into the model, the more the map converges to the true object level segmentation of the scene. Now, it is worth mentioning here that an alternative approach to perform segmentation in 3D of a reconstructed volume could be to directly use the 3D color and geometry information in the reconstructed map to try to parse which parts of the scene constitute separate objects. However, segmentation and classification performance in 3D is still falling behind compared to 2D-based image methods. Also, the fact that we, in our approach, do not require the full scene reconstruction to start detecting and segmenting objects is actually what allows us to operate in a non-line fashion. So let's take a closer look at the final reconstructed map of this office scene to inspect whether it satisfies the properties that we talked about in the beginning, namely that our framework is able to both segment and semantically label recognized instances, but also it can discover novel and previously unseen object-like elements. So here is again the top-down view of the office, and here's our final result. So again, let's take a closer look. And we can see that indeed, our framework is able to segment as one single object these highly non-convex chair elements. And importantly, more importantly, we're able to tell that these are two separate instances of the class chair, so they do not belong to each other. Additionally, we are able to discover the box-like object on the table. And while we might not know exactly what kind of object that is, we do not know its semantic class, we still know its shape and pose in the room. And this is already enough for downstream applications such as grasping and manipulation planning. And besides knowledge about which parts of the scene constitute individual instances, we also have a semantic class associated with some of the segments. And for example, here again, there are chairs shown in red. Now, this is just one scene. But if we go through many scenes of an entire dataset, and in this case, we did so with the real world CNN dataset, we're able to collect an inventory of some of the detected and recognized segmented objects. So here I'm showing some examples of instances of the class chair. I have some examples of the class couch and of the class table. But besides elements that were semantically recognized, our framework can discover entirely novel and previously unseen object-like elements. So here is just a selection of the most interesting stuff discovered that I manually picked. And we range from a jacket to a heater to a drawer. And again, our algorithm does not know about these labels and has never encountered them during training. They're just shown here for your information. Now, because this talk series is all about robotics, I feel like I'm legally obliged to show you a moving robot. So I'm going to do just that right now. The framework has been validated on a real-world robotic setup, and the setup consists of a ClearPath Reachback mobile base with on top an ABB dual-arm Yumi robot, although in this perception-only experiment, we did not make use of the two arms. And then on top of the Yumi robot, we have our sensor stack, which in the middle has a visual inertial sensor that will be used for localization. And then it has two prime sense RGBD cameras, one facing forwards and one facing slightly downwards. And we have two just to have an increased effective field of view. So the platform is manually steered through the entire office floor of our lab, and it is localized in the lab through a combination of visual, inertial, and wheel odometry, and global feature-based localization against a pre-built map of the lab. So the streams of the two prime sense cameras are processed in parallel, and at a map resolution of 2 centimeters, our framework was able to run at approximately 1 Hertz on a standard laptop. So this means that if our prime sense cameras were streaming at 30 Hertz, we had to throw away 29 of the 30 frames per second. Now, actually, this runtime performance is very much similar to the runtime performance of when just reconstructing the 3D geometry of the scene without the object level information parsing on top. Now, 1 Hertz might even be enough for some robotic applications, but of course, there is still a lot of room for improvement here. However, in this experiment, what we wanted to show is that we can indeed process in a non-line fashion, not only tabletop scenes and room scale scenes, but also building scale environments. So the final map describes the geometry of the observed scene, although quite sparsely, because as mentioned, we only use 1 RGB frame per second and throw away the remaining 29 or so. But most importantly, the map contains information about the individual objects in the scene, and it also encodes free space information, so which parts of the scene have been observed as free, unoccupied. And of course, all of this together can enable successful planning of downstream grasping, manipulation, or even navigation tasks. And if you're interested in more details about this framework, you can check out our paper or even play with the fully open source code of the framework, which we refer to as VoxBlocks++. Now, VoxBlocks++ operates on the assumption of a static environment. And a static environment is an environment in which the camera is the only moving object. And naturally, such approach does not hold for the highly dynamic real-world environments that robots share with humans or other autonomous agents. So let's take VoxBlocks++, which was originally intended only for mapping of static scenes, and feed it a dynamic scene to see what happens. Let's start with this toy sequence from a synthetic dataset that was published with the CoFusion paper some years ago. It is a very simple sequence that contains 2 toy car objects moving along a tabletop surface. Now, if we process this RGBD sequence with VoxBlocks++, we can see that the reconstructions of the moving objects are scattered all over the place. So the dynamic objects break the static assumption and leave these awful ghost artifacts in the 3D map. So hopefully this motivates the need for a framework that not only detects, recognizes, and segments individual objects, but also is able to track their motion and update the map over time to reflect it. And this is exactly what we investigated in our second work I would like to present today. So let's start by taking a look at existing frameworks for multiple dynamic object tracking and reconstruction, and in particular, the 3D map representations that they adopt. A number of works address the task of simultaneous tracking and reconstruction of multiple objects which are moving in the foreground. So these works can detect and segment arbitrary objects moving independently in front of the camera. They can track their motion and simultaneously densely reconstruct their 3D shape. And MaskerCN was perhaps one of the first of such frameworks, reconstructing both the static background and the dynamic objects in the scene. And as for map representation, MaskerCN uses separate surface clouds to represent the mapped object models. And surface clouds can be interpreted essentially as point clouds, but each point additionally contains information about a radius and a normal. So surfaces are very memory efficient, but they cannot directly provide free space information. So they cannot tell us which parts of the scene during reconstruction have been observed as unoccupied. And also they do not provide surface connectivity information. So all of these surfaces, they are not joined together by any connectivity. So the built object level maps effectively cannot be directly used for safe robotic navigation and motion planning purposes. Another framework known as MidFusion also tracks and densely reconstructs multiple objects moving in front of the camera. But in this framework, they choose to store every object in a separate volumetric grid, specifically in separate oct-tree structures, which are very efficient hierarchical structures. Each of them encodes, which then encodes the TSDF values of the individual objects in the scene. And so, just like VoxBlocks++, this volumetric approach explicitly models free space and surface connectivity, which allows one to directly use the build map for robotic tasks. So again, the map of the entire scene is essentially a collection of multiple 3D models in this framework, each with an associated pose with respect to some global reference frame. Let's illustrate this intuitively with an example. So there will be one volume for each of the cup objects, a separate 3D volume for each of the foreground objects, and then there will be, of course, a larger volume for the remaining static background. And each of these volumes will have an associated pose. So as a result, updating the map to reflect the latest estimated position of an object is as simple as updating the corresponding stored rigid transformation. Now, while simple and intuitive, such map representation can carry several limitations. For instance, each of the computationally expensive raycasting operations commonly required at each time step by the typical tracking fusion pipeline must be performed multiple times. Why? Once for every object model stored in the map. And so this scales very poorly with respect to the total number of objects in the scene. Moreover, raycasting through multiple independent volumes requires an explicit occlusion handling strategy that would allow us to determine surface visibility when one object is occluded by another. So an alternative representation could be a map that consists of a single TSDF volume, and just like in VoxBlocks++, is augmented at each voxel to additionally store information about which object instance that voxel belongs to. So then whenever an object moves, this map can be updated to reflect its latest tracked pose by simply translating the portion of TSDF values, the portion of voxels associated with that object within the volume. Now, storing the entire scene within a single volumetric grid is great because it avoids the need to raycast several volumes at each step multiple times, and it does not require an explicit occlusion handling strategy to determine which of the objects in the map are visible from the current camera view. However, a key limitation of the traditional TSDF representation is that the translated TSDF values would effectively override whatever surface reconstruction was previously stored at the destination location. So as the reconstruction of the moving objects is translated around, the reconstruction of the surface that is being occluded by the moving objects is inevitably destroyed. We can intuitively illustrate this with an example. So here we process the synthetic toy car sequence from before with a fairly standard framework for multiple object tracking and reconstruction that we propose, adopting the single standard TSDF volume as map representation, then shifting around the TSDF reconstruction of objects as we detect that they move. And we process the synthetic sequence up to frame 256, and we rely on the ground truth segmentation that is provided with this sequence. At frame 256, we stop integrating, and we then simulate the removal of the two reconstructed toy car objects to reveal the tabletop surface underneath them and verify whether it could withstand occlusion. Unfortunately, the standard TSDF representation presents two holes in the table surface in correspondence of the two moving objects, despite that part of the surface having been previously accurately reconstructed. So we set out on a quest to design a novel volumetric representation that would allow us to index the entire scene and all objects therein within a single volume, and as a result, retaining the benefits of no repeated raycasting and no explicit occlusion handling. But that additionally would be able to preserve reconstructed surfaces even if they become temporarily occluded by other objects moving nearby. So this is exactly the contribution of our latest work at ICRA, which is called TSDF++, and it is a novel map representation that is well suited for the dynamic object tracking and reconstruction task. The key idea behind the TSDF++ formulation is that it allows to store at each voxel multiple implicit object surfaces. We can illustrate this with an example in 2D. So intuitively, the proposed TSDF++ formulation can be interpreted as a layered volumetric representation, with the first layer encoding the visible object surfaces and the remaining layers storing the surfaces of objects that are currently occluded by the visible ones. In practice, the TSDF++ representation is implemented as a collection of multiple smaller TSDF volumes, one for each mapped object model, which are all indexed via a global volume, the global TSDF++ volume. Each voxel in the global map then keeps track of which object model is active at the corresponding 3D location and which object model, if any, is inactive or occluded. And then the individual object volumes encode the actual TSDF of the corresponding object geometry in a common coordinate frame and share the same resolution as the global map volume. As a result, given voxel in the global map volume, the corresponding TSDF voxel in one of the object volumes can be directly accessed using the exact same grid coordinates in constant time. Now, let's see our proposed representation in action and verify whether it satisfies the desired properties mentioned earlier. Here again, we evaluate the ability of the proposed map representation to preserve a previously reconstructed surface during occlusion on the synthetic toy car sequence. Once again, we process the sequence with the proposed framework for multiple dynamic object tracking and reconstruction up to frame 256, this time relying on TSDF++ as map representation. We then simulate the removal of the two toy car objects and inspect the tabletop surface and correspondence of the two removed car. We observe that our formulation is able to preserve an accurate reconstruction of surfaces, even if they become temporarily occluded by other moving objects, and all this while maintaining a single volume for the entire scene. Now let's briefly take a look at the full pipeline that we propose for the multiple object tracking and reconstruction task, into which we then plug TSDF++ as map representation. So firstly, we propose a per frame segmentation step, just like the one in BoxBlocks++, that essentially takes an input RGBD pair and extracts from it segments which represent foreground objects which are potentially moving and that need to be tracked. Compared to BoxBlocks++, however, here for simplicity, we choose only to consider those object segments which have been semantically recognized or semantically labeled. So we leave out the novel and newly discovered object-like elements. We then make the assumption that the objects moved only a little bit since the last frame we processed. And we use this assumption together with the known camera pose to associate the extracted 3D segments in the input frame to the 3D object segments in the map, to then actually try to align them and estimate the rigid transformation of the object between the current and the previous frames. And this, of course, happens for every one of the semantically detected objects in the current frame. And finally, once the rigid transformation for an object is estimated, the map of the scene needs to be updated accordingly. Since the proposed TSDF++ representation stores all of the mapped object models within the same grid and coordinate frame, updating the pose of an object requires actually translating the corresponding TSDF values within the tracked object volume, and of course, updating the global map volume to reflect this change. And once this is done, we can additionally fuse the geometry information for that object that was just observed in the current frame. The proposed formulation does unfortunately introduce a couple of limitations. First of all, because now to update the pose of an object in the map, we have to actually translate the TSDF reconstruction within the corresponding object volume, we introduce interpolation of the reconstructed geometry, which inevitably leads to less accurate reconstructed object geometries. Next, because we are focusing a lot of memory usage now to resolve over time which surfaces are visible and which temporarily occluded, we dedicate less memory and computation to actually resolving ambiguity in the per frame object segmentation step. And this leads to slightly less accurate 3D object segmentation results in the map, and in turn worsens slightly the object tracking performance. To illustrate this, we process the same toy car sequence with the proposed multiple dynamic object tracking and reconstruction framework and the novel TSDF++ map representation, but this time we get rid of the ground truth segmentation and introduce the per frame geometric semantic segmentation step. We can observe that inaccuracies and misdetections in the per frame segmentation scheme do in fact negatively impact the reconstruction and 3D segmentation results in the build object level map. Nonetheless, whenever objects are correctly detected and recognized, their pose is successfully tracked and their shape is reconstructed over time. Once more, you're welcome to read more about it in our paper or play with the fully open source code of the framework. So in summary, today we have shown a framework to incrementally build dense maps that contain information about the semantics in a scene at the level of individual objects. We could map both recognized as well as we could discover previously unseen elements in a non-line fashion, even at a building scale. We have demonstrated how object awareness can improve other related perception tasks, such as multiple dynamic object tracking and reconstruction. We propose the SDF++, which is a novel multi-object volumetric map representation that can store multiple implicit object surfaces at each voxel in the map. And the entire scene is indexed by a single global volume, removing the need for repeated breakcasting and occlusion handling, and making the representation well suited for the multiple dynamic object tracking and reconstruction task, because it is able to preserve surface reconstructions even if they are occluded by other moving objects. And in general, we believe that the ability to perceive the environment at the level of individual object instances can bring new possibilities to several other perception tasks. For example, we are currently investigating working with transparent objects in 3D. So transparent and reflective objects are a classic struggle in robotics because traditional depth sensing fails to provide the accurate and complete geometries of the observed transparent surfaces. Even when the geometry of the surfaces is properly estimated, the 3D scene only contains the parts of scene that have been actually observed by the sensor. So we are currently playing with the idea of estimating the visible surface geometry of the transparent objects, which has been already partially solved by other frameworks such as Clear Grasp via deep learning. But additionally, if possible, estimating the invisible surface geometry, so beyond what is visible from the sensor during scanning. But yes, this is a truly relevant and interesting research direction, which would increase robustness of many downstream robotic tasks when working with transparent and reflective objects. And I hope to be able to share some results with you soon. In the meantime, I will be happy to take any questions if there are any. Thank you.
Thank you very much, Margarita, for the great talk. Are there any questions from the audience? If yes, you can unmute yourself. It was too clear of a talk. I have a small question. Maybe what I'm asking is not relevant at all, but in the most recent part of the talk, you mentioned that you use basically you reproject back the images you capture with the transformation, the extrinsic calibration of the camera, or the camera to body transformation. My question is, typically these frameworks capture many images, and the images are taken from cameras that are calibrated in different ways at different moments, might have some shifts or some wrong calibrations. How does wrong calibration or systematic wrong calibration influence the scores of your map accuracy? Mm-hmm. Does it even play a role?
So I assume you're talking about when we extract essentially the new frame, the geometry of the current frame that we're observing, we of course are relying on the calibration of the depth sensor, but also perhaps of the color sensor, just to be able to perform the 2D overlap between the color and the depth frame. And then if these calibrations over time change, or we didn't calibrate them accurately enough, how this then, which effect does this have in our reconstruction or segmentation results?
Precisely, yes, exactly.
So I haven't played with, you know, on purpose worsening my calibration. So I cannot answer exactly on that. But what I can tell you is that we are, we are observing much larger problems, perhaps, which have had much larger impact, and that is odometry drifts, or the camera pose. We assume that is perfect, right? But of course, third-party modules, or even the pose that is sometimes provided with the data set as ground truth, has been computed by some other framework, and this some other framework, of course, has its own, jumps and errors, and so this actually has a lot of impact in our maps. So perhaps I can show it in the video here. So in this framework here, in this experiment here, towards the end, when the sequence essentially returns back to original point, there has happened a lot of drift, and you will see this because some of the armchairs that were constructed here now will be essentially overwritten and re-reconstructed again, just because there was a drift of at least 1 meter, I would say. So yeah, we deal with this kind of errors, and they negatively impact our framework. And I guess that calibration would be similar to this, in the sense that just the 3D points of the current frame are not where you imagine them to be, in the same way as with the odometry. And so, yes, the impact, we didn't compute any numbers as to like how much, but definitely it's something that, yes, impacts us a lot.
Okay, great. Yeah, I imagine there was an impact, and I wanted to know if you are making up for them, are compensating for them in some way.
No,
Great.
not yet. We're just relying passively on the localization performance of some other module. We are not actively trying to correct it or compensate for it.
I would have a related question, Gabor here. So is there any other technical limitation other than this pose estimation, if to use multiple cameras at the same time, or use a model that you created, let's say yesterday, and then relocalize that camera, a new camera again, and rediscover, and you need to align them somehow. But is there any other technical limitation than just a pose registration?
So you're saying if I want to introduce two cameras,
perhaps two robots at the same time, yes.
Two robots that are not calibrated with respect to each other, like in the two cameras in this example, and would there be any technical limitations besides registering them against a global coordinate frame?
Yes. So the TSDF could actually handle multiple inputs, right?
Absolutely. I'm only thinking if we are really talking about different days, perhaps the scene changed. And so what would happen is that the camera that comes later in time would end up erasing some of the, for example, if there was an armchair in the middle of an office, the first camera reconstructed in the map, and the second camera would come and it would have conflicting observations. It would say it's empty. And then over time, the TSDF would essentially be eroded and the new empty space will be reconstructed there. So apart from this kind of, we're not resolving conflicts in the sense that we're not doing any change detection, because we're assuming a single robot, a single sensor stack. But yeah, I don't see any other limitations besides this.
Okay. I was thinking about something like a ground robot and a drone. So some of the viewpoints are more reliable, let's say, from the top view, some from the bottom. But yeah, we can think about these things.
Yeah, you're right. So actually, in this sensor stack here, why we have two cameras facing forwards and slightly downwards is actually because we noticed that now, in the context of this experiment, it doesn't matter, but for other experiments, such a mobile platform needs a top-down view to, for example, perform a tabletop tasks. You know, seeing from the top is much more informative than seeing a table and the objects on it from the side. But actually, perhaps localizing against walls or localizing against furniture that is on the sides of the robot is much more convenient with the camera that is facing forwards. So I guess it's we're going in the similar direction that the one you're mentioning here with this sensor stack, essentially.
Okay, thank you. Very cool work. Thank you.
Thank you.
Any other question?
Rita, can you explain again what a circle is?
Mm-hmm. So circles are essentially, so one circle is one point that is characterized by a 3D position, so XYZ, And then you can imagine it as a small disk. So it has a radius and a normal information. And if you place enough of those disks, right, that are kind of splattered all over the surface of an object, with the human eye, they're very nice to look. They're quite nicely distributed.
Right. I understand the normal. That's nice. That's interesting. But the radius, why would you want the radius? Just for the visuals.
Yes, just for
the rendering, kind of in a sense, right?
That's why I'm saying circles are very pleasing visually, but yes, they're not very useful directly for robotic tasks. That's exactly the thing.
But I would think that the normal information could be useful, right?
I mean, I'm not saying they're completely useless. I'm saying that they're missing a key piece for safe planning. For example, if you just tell me that I reconstructed a table and I know the surface of the table, but I have no idea whether you observed the area around the table. And can you tell me whether it's free for the robot to navigate? Is there free space around it that I can use to traverse the scene? All of this is missing there.
Okay, cool. Now, when you do, so you keep track of the ID of an object?
Yes, absolutely.
So when you have occlusions and you don't see something for a while, you recognize it's the same, or you just say that it's a chair that looks like the other chair?
No, we do keep track. And this is, of course, made possible by the fact that we have a camera pose provided to us. So essentially, if you revisit a scene after a while, you know where you are, right? Because the camera pose told you.
Okay, but that works in a static environment, right?
Yes.
So, but for example, in the video, you were showing like a moving object, right? So would this work also in a dynamic environment where your objects can move?
Yes, so I guess this would be then a matter of using the second framework that I propose, which is actually intended for dynamic objects. And in this case, once more, if the objects, if they left, right, if from one day to the other they travel on their own somewhere else, then we have a conflict there. And it's not about object tracking anymore. It's called more change detection. But as long as we're talking about objects that are moving and are being observed by the camera while they are moving, then this is a problem for us. And we can track their motion, assuming they do not move, 100 meters in 1 second. We can track their motion and using the known camera pose, using the fact that, yeah, it moved, but not too much. So there's still a lot of overlap between what I observed and what was in the map. So I can kind of associate them by propagate the ID from the map to the current frame, and then I can do the ICP step.
But for that, you need some kind of a model of the motion of the thing that you're not seeing.
I think it's just enough. I mean, you could incorporate a motion model if you want to kind of bootstrap your ICP step, but assuming that the objects did not move enough, you will have a set of points that describe where it was.
No, I'm asking because I have a very specific use case in mind. That is, so for example, think of cars, right? And then when you get to intersections, at least in the US, you have like a four-way stop. Then the order of precedence is the same as the order of when the people got to the to the stop and they stopped at the stop line, right? So, but what can happen is that somebody is getting to the stop line, then they get occluded by, say, a bus or a truck or something. Then the truck goes away. You need to know who that car was, because you need to know, because that establishes the precedence. Right, so that's why I had that particular use case in mind.
I see what you mean. I perhaps believe that I don't know if I lost you for a second. I don't know if I'm still on.
I can hear you.
Okay.
You're kind of frozen, but I can hear you.
Yeah, so I think this is exactly in the scenario of the things that we cannot do, because if you're saying that the bus is occluding the car and then the car is moving without my sensor being able to see it, that I cannot track it. I cannot guess where it's going to go. I mean, then, yes, what you're saying, a belief of where the car is going to move and at which speed might be very useful to kind of track without seeing, behind visual line of sight. So beyond visual line of sight, yes. Then in that case, it will be very useful.
Thank you, Margarita.
Any final question? Doesn't seem so. Thank you very much, Margarita. I think you gave your contact in case people want to reach out for deeper questions.
You can just Google my name and be able to find.
I just want to make sure. Thank you very much for the talk and good luck for the next steps.
Thank you very much. It was a pleasure.
Great. Thank you all for participating.
Thank you,
See you all
Margarita.
next week.
Bye-bye.
Bye-bye.